Hi, this is the beginning of Psychrometrics lectures, and these lectures are. Hi, this is the lecture series on psychrometrics. These lectures are meant to prepare students for the principles of building energy analysis course. In these lectures, we will cover the concepts of ideal gas mixtures. We will talk about the partial pressure, absolute humidity, relative humidity, dew point temperature, and the enthalpy of moist air. Okay, moist air is what we live in and what we breathe. Air that we breathe contains water vapor. That's why we call it moist air. This is different than what we learned about air in the introductory thermodynamics course, in which the air is considered as a pure substance. There's no condensation of water vapor if you cool a pure substance ideal gas air. However, in air conditioning, the water vapor may condense, and you may also add water vapor to a moist air so that you can control the moisture content or the water content in air to achieve the desired condition. In psychrometrics is a study in engineering that's concerned with the determination of physical and the thermodynamic properties of moist air. In psychrometrics, moist air is simplified as an ideal gas mixture of dry air and water vapor. This table summarizes the important relations when we talk about the ideal gas assumptions for the moist air. So, as we said just a moment ago, moist air is considered a mixture of dry air and moist and water vapor. Both are ideal gases. So, instance they're both ideal gases, then we can apply the ideal gas equation of state to each of the components, dry air and the water vapor. And also, the moist air as a whole should also follow the ideal gas equation of state. And then in this table, you can see we have several variables. We have P sub A, P sub W, M sub A, and M sub W, and also capital M sub A and capital M sub W. These are, I forgot to include the variable capital M sub A and capital M sub W. These two are, capital M sub A or capital M sub W, these are the molecular weights of dry air and the water vapor. And then you can see these are the ideal gas equation of state. And in the second row, you can see here we introduce this concept. It's called absolute humidity, or humidity ratio, or specific humidity. There are several different names for the same thing. Essentially, what this is, omega is defined as the ratio of water vapor mass to the dry air mass. And then when we realize that, we can express the ideal gas equation of state for water vapor and the moist air using the specific humidity or absolute humidity. There's also a term called the water vapor molar fraction. This is basically the mole fraction of the water vapor in the moist air, which we can easily find that it's the ratio of these two things. It's the ratio of this x is equal to M sub W divided by capital M sub W, and then this divided by M divided by it's the total of these two. Okay, so that's the molar water vapor molar fraction. Okay, and then you may ask, what is the definition of partial pressure? The partial pressure is, imagine this: you have a moist air in the container, a rigid container. It's also airtight if you can control that so that the molecules you can pick out of the container and then keep it out of the container. So you have that control. If you can take all the air molecules out of that container and you only leave the water vapor molecules inside the container, it's rigid and it retains the constant pressure, constant temperature. Because there are fewer molecules in the container now than the pressure exerted by the gas molecules in bombardment on the surface of the container, inner surface of the container, will be smaller, and that pressure is called the partial pressure. It's due to the existence of the water molecule in this system. On the other hand, you can also keep the dry air molecules in the container while taking the water vapor molecules out of that rigid container, and then you have a smaller pressure than the total pressure as well, and that pressure without the water vapor molecules, is called the partial pressure of the dry air. Okay. So here we defined, previously we introduced the absolute humidity. It's also called the specific humidity or humidity ratio. That's the ratio of the water vapor mass to the dry air mass in a moist air system. We can further write this expression, this ratio, in terms of the ratio of the partial pressures. So this is essentially 0.622 water vapor partial pressure divided by the dry air partial pressure. Now, here I have a question for you. What is the where does the constant 0.622 come from? And you can go back to that table that I showed you previously, and you can figure out where this comes from. We also often use the concept and the quantity that's called the relative humidity. Relative humidity is different than the specific humidity. It's related, but it's very different. The relative humidity is a ratio of the actual water vapor content. It's the ratio of the water. Actually, I should change this to the actual water vapor partial pressure. It's the actual water vapor partial pressure to the maximum water vapor partial pressure. So that we avoid some ambiguity. So it's the ratio of the actual water vapor partial pressure to the maximum water vapor pressure that can exist in your system. What is the maximum water vapor partial pressure that can exist in your system? It's actually the saturation pressure of the water vapor corresponding to this particular temperature of your system. Okay. We also use a concept that's called a dew point or dew point temperature. So suppose you have a moist air that doesn't have 100% relative humidity. Now you can cool that moist air and then cause the temperature of the moist air to decrease. And based on your experience, at some point the water vapor will start to condense from the moist air. And that temperature at which the first drop of water condensation begins to happen is the so-called dew point temperature. Okay, so it's actually the temperature corresponding to the dew point temperature is the saturation temperature of water vapor for your water vapor partial pressure existing in your system. Okay, so imagine using the saturation table. You can find the partial pressure of water vapor in your system, and then go to the saturated water table, and then find the saturation temperature corresponding to your water vapor partial pressure, and that is the dew point temperature for your system, for your moist air system. Conversely, the water vapor partial pressure in your system is equal to the saturation pressure of water vapor corresponding to the dew point temperature of your system. All right. So let's look at two examples to help understand the relative humidity and the dew point temperature concepts. If we know that moist air is at 25 degrees Celsius and with a total pressure of 1 atmosphere, and the partial pressure of water vapor in this system is 2.3393 kilopascal. All right, we need to find the relative humidity of this in this system. The assumptions we use is the normal assumption for psychrometrics. Moist air is ideal gas mixture of dry air and water vapor, and the maximum water vapor partial pressure is the saturation pressure at 25 degrees, which is the temperature of your system. And we can find that saturation pressure from the thermodynamic property table, which is 3.1699 kilopascal. The relative humidity is the ratio of your actual water vapor partial pressure to the saturation water vapor pressure at your system's temperature, and therefore is 2.3393 divided by 3.1699, which is 73.8%. All right, dew point temperature example. If we know on a particular day at 9 p.m. In College Station, Texas, the air temperature is 22 degrees Celsius, and the total pressure is 1.0102 bar, and we know the dew point temperature is 16 degrees Celsius. And if you look at a weather forecast, you often find the dew point temperature being reported. So here we want to find the relative humidity, the absolute humidity, and the molar fraction of water vapor in the air, knowing the information above. Okay, so the assumptions are still it's an ideal gas mixture of air and water vapor that we're dealing with, and the maximum water vapor partial pressure that can exist in the air is the saturation pressure at the particular temperature of your system. All right, here we look for the relative humidity first. Relative humidity, we need to get the actual partial pressure of water vapor in the system. We were given the dew point temperature for the system, which is 16 degrees, and we know from the definition of dew point temperature, the actual water vapor partial pressure in the air system, in the moist air system, should be equal to the saturation pressure at the dew point temperature, which is 16 degrees Celsius. And we can find that from the thermodynamic property table, and that turns out to be this. So now we also know the maximum water vapor partial pressure is the saturation pressure at the actual temperature of the air, which is 22 degrees Celsius. And we can also find that saturation pressure corresponding to this temperature, and that is this value. So the ratio of the two will give you the relative humidity. And as for absolute humidity, we can simply use the equation that we have seen on a previous slide, which is this. Is the 0.622 partial pressure of water vapor divided by the partial pressure of dry air. Okay, and the water vapor partial pressure was found here. So we can use that equation to calculate the absolute humidity. And the molar fraction of water vapor can be simply found by dividing the partial pressure of water vapor by the total pressure, and that gives you the molar fraction of water vapor.